Alright, welcome back everyone. Today we're going to be learning a little bit more about limits, specifically techniques on how to compute limits analytically. So last time we began talking about what limits are and how to estimate them. So let me start by writing a few things. So last time we began, recall, last time we saw how we can estimate limits graphically or numerically, as we did last time. Now, these techniques, while useful, can occasionally lead to incorrect results. So we will discuss now methods on how to compute limits analytically. If we compute limits analytically, then we'll have a precise value for our limits. So let's begin by talking about the limits of linear functions. Recall that a linear function is a function of the form y equals mx plus b, and the graph of a linear function is a straight line. So that's something that we should all remember from pre-calculus. So recall that a linear function is a function of the form f of x equals mx plus b, and represents the graph of a line, straight line, with slope m and y-intercept b. We saw this during the review as well, the pre-calculus review that we had earlier in the semester. Now, let's say we had some linear function. So let me really quickly do a plane. So let's say we had some linear function, this is y, x, my origin. So let's say we had some function, it's a line, let's call it f of x. It's increasing from left to right. And let's say we had here some point A. Well, A on the x-axis, if we plug it in for the function f, is going to have some output, and that output will be somewhere up here. So this will be the point corresponding to a comma f of a in the output. So this will be our x coordinate, this will be our y coordinate. Well, from what we learned last time, as we approach a on the x-axis from the left side, these numbers here, these x values here, 0, negative 1, 1, 2, and so on, they all will have outputs on f of x. If we plug them in, we will see the output values, and they're traveling along the line. And we can notice that as we get closer and closer to a from the left and the right side, the x values, the y values actually are approaching this number right here, which in this case is f of a. So it turns out that the limit as x goes to a of f of x is actually equal to f of a. And we could see that, you know, if we travel along this line from the left side and the right side, we will see that the left-sided limit is going to be f of a, whatever that number is, and the right-sided limit is going to be also f of a. So that means that the limit of f of x as x goes to a is precisely the value of the function evaluated at a. So it follows from this idea that for the limit of a linear function, you could simply find it by directly substituting the value of a that we're limiting to into the actual function. So let me write that down. So it follows that for linear functions, the limit of f of x as x approaches a is found by direct substitution of x equals a into f of x. And this leads to the following theorem, which I will not be proving in this class. Let me actually write like this. So theorem. So if I write from now on, because we're going to have a lot of theorems in this class, I'm going to be denoting theorem with THM. So it's the first two letters of the word and the last one. So if you see me just write THM, that just stands for theorem. So the limit of linear functions, that's what we'll call this this theorem. And it says the following. It says that let a, b, and m be real numbers. For linear functions, f of x equals mx plus b, we have the following. We have the limit as x goes to a of f of x equals the output value f of a, which equals m times a plus b. So this is the limit as x goes to a of f of x equals f of a, which equals m times a plus b. And this should not come as a surprise, because this is just a direct application of the definition of a linear function. We plug in, so we have limit of x goes to a of f of x. What we're doing is we're taking this value right here that we're limiting to, and we're plugging it in for f. So we have f of a, but remember what f was. F is mx plus b, so we have m times a plus b. So that's where we're getting this from, this ma plus b. So whenever you're given a linear function and you're asked to evaluate a limit, you could do it analytically by simply substituting in the value wherever you see an x. This is much simpler than estimating by using a table like we were doing last time. For example, if I ask you what is the limit as x goes to 2 of 2x plus 4, if you told me what this is, if you ask me what this is, then all you have to do is substitute 2 wherever you see an x. First of all, let's identify that this is a linear function. This is y equals 2x plus 4. That's a y-intercept at 4, slope is 2. So we could simply substitute, as our theorem says, substitute this 2 inside and add 4. So we have 2 times 2 is 4, and 4 plus 4 is 8. So we have that the limit as x goes to 2 of this linear function is 8. And this is much easier than creating a table and finding out what the value of 1.9 is, and 1.99 and 2.001 and so on, simply to estimate this value we're going to get. If we were to estimate, we would get a bunch of 7.999s and 8.0001 and so whatnot. So we could try this. So let's do some examples, some more examples of this. Examples. Let's evaluate the following limits. So the first one, let's call it A, it's going to be the limit as x goes to 3 of f of x, where f of x is the following. F of x equals 1/2 x minus 7. Again, our theorem says that if we have a linear function, then it suffices to simply plug in the value that we're approaching, the value of a that we have, into the actual function. So what do we have here? So we have f of x equals 1/2 x minus 7, and I want to find out what happens as x goes to 3. So what I'm going to do is I'm just simply going to plug in 3 into my function. So I have 1/2 times 3 minus 7. Again, this is limit as x goes to 3. Right, so what do we have here? So we have 3 times 1 is 3, 1 times 2 is 2, so we have 3/2 minus 7. You can simplify this a little bit more. You can multiply the 7 by 2, so you'll have negative 14 over 2. And if you do 14 minus 3, then this will be negative 11/2. So we have that the limit of f of x as x approaches 3 is equal to negative 11 over 2. So this is much simpler than trying to plug in and estimating values for the function. If you were to plot this function, you will also notice that the limit calculation that we did is completely correct. So you can also still plot it and verify your work. Let's do another one. So let's do another one. So we have limit as x goes to 2 of g of x, where g of x equals 6. Okay, so what do we have here? So we have the limit as x goes to 2 of g of x. Well, what is g of x? G of x is 6. So we have here is limit as x goes to 2 of 6. But by our rule, this is also a linear function. If you remember, from pre-calculus, this is the same thing as having y equals 0 times x plus 6. So that's a linear function. By our rule now, we could simply evaluate g of 2. But g of 2 is 6 because there's no x's here. So no matter what x value we have, we always have 6 as the output because it is a constant. There's a constant function. If you don't believe me, simply graph it. Y equals 6 is just a horizontal line at y equals 6. So it doesn't matter what value you have for x, whether it's positive, negative, or 0. you always get 6. So the limit is 6. And this is going to be the case for every constant that you have. So this is actually a fact. So fact limit as x goes to c of some number, let's call it b. So it's going to be equal to b for b, c, and x being real numbers. So if b, c, and x are real numbers, then this is always true. The limit of a constant is simply the constant. Okay, so this is the first big rule that we have when it comes to evaluating limits analytically. What I'm going to do now is I'm going to give you a bunch of laws. It's about 7 of them, technically 8, that will really help us simplify our process of evaluating limits for any type of function that we are given or that we may come across. Okay, actually, let me try to grab my keyboard from there. Put this down. All right, so let's see. So, theorem, these are the limit laws. Let me try to make this finer. Okay, so let's assume, first of all, assume the limit as x approaches a of f of x, and the limit as x approaches a of g of a, or g of x, exist. Then the following properties hold. And note, c is a real number, and n is going to be a positive integer bigger than 0. Okay, so we have the following. So we have first the sum law. This is the following. It says that if you have the limit as x goes to a of f of x plus g of x, then that is equal to the limit as x goes to a of f of x plus the limit as x goes to a of g of x. So we can break up this operation and take the limit independently. If we could take it first with f and then with g and then add it together, or we could do it all at the same time. So if you're given two limits as a sum, like the limit of f of x plus the limit of g of x, then you could combine it, so long as they're approaching the same number, the same value a. You can always do this. Number 2,